Hello everyone. I just made a video a few hours ago talking about a realistic modeling and simulation of a projectile with only air drag, where the air drag was modeled accurately with, or relatively accurately, with allowing the coefficient of drag to change as well as density of the air. And I said to myself, let me show the audience, really the fans, something a little bit more interesting. So here, not only I want to use the previous simulation, I want to let the ball hit the ground, or the projectile hit the ground, and then bounce back and bounce back and back and back until it loses all of its energy and literally doesn't bounce back. Okay, so I want to do that. And a bonus sound effect. I want to also add a bonus sound effect for you. So when the projectile is shot, I want to basically add some explosion sound to it to make it really nice. So how do I model the rebounding? So all you need to do is when it hits the ground, where y becomes what? Where y becomes negative and your Simulink is gonna stop right here, you're exporting not only x and y at all time, you're also exporting x dot and y dot, the components of the velocity. And when the ball hits the ground, one of these components is going to be updated. Okay, which component? Well, let's take a look. So here is the ground, and the projectile comes and hits the ground like that with the two components x dot and y dot before impact, and it comes here at angle like that, and the line of impact is the y-axis, right? So along the y-axis the velocity will change, but nothing along the x-axis, right? So with the same x dot, if you call it x dot before, the x dot after is going to be the same as x dot before, because there is no force exchange along the x direction. Along the y direction, it is going to bounce back with a smaller velocity. You might call it y dot after. And how is these two y dots related? Using the coefficient of restitution, E. And as you know from my dynamics lecture, this is between 0 to 1. 1 means no energy is lost, which is not super realistic. 0 means the projectile basically gets stuck to the ground and doesn't bounce back. So here I go with some number between them, which shows the loss of energy as well as rebounding. And so I'm going to use these two equations. So anytime that the y becomes less than or equal 0, I'm going to restart my initial conditions. So I'm gonna run my Simulink file over and over in a loop, where each time I'm going to what? I'm going to update my new x dot and new y dot. How? I said the x dot to start your Simulink is the x dot before the Simulink was stopped, and the y dot to start is the y dot before you stop it times negative e. Another thing you have to do is to update your launch position. This x0 and y0 at the launch position are going to be updated. If you start from here and you go like that, if initially, let's say x0 was 0 and y0 could be 0 or non-zero, right, in general, now when it hits the ground and bounce back, then what? Then this time definitely your y dot has to be 0, and x dot here is going to be the last x of what? Of the previous simulation, the previous time in the loop that I ran the Simulink file. Okay, so I have to look at the last x, and from there I would start my launch position. Okay, I'm not going to go back at the origin and start, right? From the point that it lands on the ground, that is going to be my new launch point. So this is what I have done here in the MATLAB code. If you can see, all of the X and Y data that I'm going to show you later for the simulation and plot, I'm going to start with empty. And then I say, as long as the absolute value of y dot is bigger than some small number, keep doing it. So when y dot goes less than this small number, I assume that it is literally not bouncing back. If you want, you can make this even smaller. Okay? So as long as it's bigger than 0, but remember, it is always going to be bigger than 0 after the update. So it takes forever to go to 0, so you have to come up with a small number. And to me, 0.1 is more than enough, you'll see. Even you can go a little bit bigger because you can barely see anything after 0.1. So as long as my y dot, and how much did I start my y dot? With v naught sine of the launch angle, of course. As long as it's bigger than 0.1, keep running the Simulink. Get the x and the y data of the Simulink, and the second column, which are actual x and y values. The first column are the times. Store them into xsim and ysim, and then add this xsim and ysim to what? To the previous stored values of x and y. Okay, if I don't do that, anytime that this Simulink file is running again, the new x and y of the Simulink will overwrite the previous x and y, and so if you don't store them, you'll lose your data. So here I start with empty storage. Every time I get this data x and y, I'm going to store them into x store and y store. So this x storage and y storage gets bigger and bigger over simulations. I also get the x dot and y dot values, and you see here the x0 is the x of the simulation at the very end. This is what I told you. You start from where it hits the ground at the end of the range of the projectile. y0, you don't change it because your y0 was 0 to begin with, and after impact, again, it's going to be 0. But if this one was not 0, if you did not start from the ground, if you started a little bit off the ground, maybe something like, let's say what, like half a meter, okay? So you started half a meter above the ground or 1 meter above the ground, then here you need to start your y0 at what? At 0 after you run it first time. Otherwise, it is gonna start again above the ground. And look, x dot that you start with is the last x dot that you had right before stopping the simulation, before hitting the ground. And y dot that you start with is negative e times y dot right before hitting the ground. So these are updating the initial conditions. I can add them for you. These are updating the initial conditions. Okay? And you store all the data, and finally you come down here to the simulation, and the animation and everything is the same. The only thing I have added to make it a little bit nicer for you as a bonus is I downloaded a file called explosion.wav, and I read it in to MATLAB using audio rate command, and it gives you the signal and the sampling frequency, and then I use the sound command to play it with that same frequency, okay? And this plays an explosion sound when the projectile is about to be launched, okay? So I just made it a little bit nicer for you. So let's go ahead and run it, see what you get. So it takes a little bit of time because you are running that large Simulink file several times until y dot does not, in maximum, in absolute value, does not go above 0.1. You have to what? You have to run that. And you have to keep storing x and y. There we go. There we go. That was the explosion. Now the projectile is flying off. You see, that's the first time. It comes here, it hits the ground, and then another time, and another time, and another time, a few more times, and then literally it stops here. Okay, so you see here, there we go, the rebounding, another time, another time, another time, and this last time you can barely see it. Okay, these last few times you can even barely see on this scale, right? So it was really, to me, it was an exciting demo because it has the rebounding and it has explosion. Let's just look at it one more time. Here we go, and feel free to play with this animation. I give you the download link under video description for both the MATLAB file and the related Simulink. The Simulink is the same as my previous video. The Simulink is no different. It's just the M file that is different, and hopefully you enjoy. You can even add some picture of some explosion here at the beginning if you want to make it even more interesting, but I would rather not go any further, or each time it hits the ground you can add something like a basketball or something, or some object hitting the ground and bouncing back. You can even add those sound effects and make it more interesting. So hopefully this video was useful to you. I'll see you in the next lecture.